So, hello everyone. So, in this seminar, I will talk about non-perturbative determination of spin-spin interaction in a finite temperature QCD medium, QGP medium. So, this talk will be on this work is in preparation with these collaborators, Dibbendu, Olaf, and my supervisor Sayantan Sharma. So now this plot we have seen multiple times in this school that in heavy ion collision, at very early stages, quarkonia produces below zero point 0.1 Fermi, so at very early times, and they evolve throughout the evolution of the medium. So the medium just expands and it interacts with the medium. So this is a very good probe to study the properties of QGP medium because it is interacting, so it will encode all the information of the QGP medium. So now, so as introduction to non-relativistic QCD is quite successful and to describe a heavy quarkonium system bound state at zero temperature. But for Charmonia-like system, when the velocity is larger than bottomonia systems, charm cause, the relativistic effects become very crucial. So we need to take the relativistic corrections into account. These are studied in lattice. So to reconstruct the Charmonium spectral function, so a spectral function will incorporate all the physical properties of the system. So to calculate it, the Charmonium spectral function, we need to determine accurately the interaction potential of a CC bar pair. So to reconstruct that, we need to calculate the relativistic correction due to spins non-perturbatively. So these are some results so of the hyperfine splitting between for let's say bottomonia, so upsilon and eta b. So the experimental result is 61 MeV, and this spin potential have been calculated in lattice at zero temperature, and it can explain the data up to 46 MeV. And for charmonium systems, the experimental results is 116 MeV. The difference between the bound state mass of Jepsi and eta c and the lattice, if we use this lattice results, so it can explain up to 108 MeV. So we need to take the spin-spin interaction into account. But this spin-spin interaction potential at finite temperature QGP medium have not studied yet. So we have to first study from first principle lattice QCD calculations. So another motivation is that we have heard multiple times that Matsui and Saad proposed the sequential suppression of quarkonia, but there is no distinction between pseudoscalar and vector states. So when they will melt or they will melt at the same temperature or at different temperatures. So we want to pose this question that do pseudoscalar and vector quarkonia get suppressed at different temperatures? This only can be addressed if we calculate the spin interaction potential at finite temperature. And as a consequence of that, if we can calculate the spin interaction potential at finite temperature, and so we are adding the relativistic corrections to the non-relativistic predictions, so we can accurately calculate the Charmonium spectral function for vector channel of vector Charmonia. And so this will improve the dielectron production rate estimate, theoretical estimate in QGP, because this dielectron production rate is proportional to this Charmonium spectral function of vector states. And in our earlier studies, we have published it last year. So the long distance excitations of QGP, like pseudo particle states, QQ bar pair, they are non-perturbative, and for them the spin interactions remains important up to around 160 GeV. So we need to calculate the spin interaction potential non-perturbatively. So how can we calculate the thermal potential in real time, as mentioned by Dibbendu in his talk 2 days ago, that if we are treating the, we want to extract the potential energy between a QQ bar pair in finite temperature QGP medium. So as they are heavy, so we can treat them as a static. So this to calculate the potential, we have to create a quark anti-quark pair separated by some distance r and evolve in the real time and then annihilate this. So the operator goes like this. So and the expectation value is calculated on a thermal medium. So this phi is the quark and chi is the anti-quark, and this gauge link is multiplied to make this operator gauge invariant. This creation operator gauge invariant. So we are creating the operator and destroying it after evolving in time. So thermal potential can be defined if we take this logarithm of this operator of this amplitude and taking a partial derivative and in the large time limit, because potential is defined in the large time, is independent of time basically. So if we can treat the heavy quarks in non-relativistically, so then these terms will drop out if we consider fully non-relativistic system. But we want to incorporate the effect of spin, so we or in incorporating the relativistic effects, correction. So we need to take them into account. So this if in NRQCD Lagrangian, this part is the usual QCD Lagrangian for light quarks and gauge fields, and this part is for quark fields, and this part is for anti-quark field. So here this D are the covariant derivatives, and this B is the magnetic color magnetic field. So if we calculate this expectation value with this Lagrangian and take this limit properly, we will get this potential. So in due to the quark anti-quark pair both have mass m, the initial leading order this will be 2m, and the next correction next will be the static potential. So which was already mentioned by Dibyendu, and at the next leading at the next order, the spin interaction potential will come into account, which is suppressed by 1/4 times the heavy quark mass square. So the static potential is like you have a quark anti-quark, but the quark anti-quark is just scalar particle, let's say. So now as the spins are introduced, this will incorporate the relativistic effects. So now the static potential is defined the log of the Wilson loop. So in the next slide I will I will show you the diagrammatic way. And the spin potential have two components. This is a interaction term, and this is self energy term of the spin interaction. So, but to calculate this operator non-perturbatively, we need to calculate this in lattice QCD. And lattice QCD, as heard in the talk by Somen Datta, that lattice QCD is defined in a Euclidean spacetime, and we discretize the Euclidean spacetime. So we have a finite, uh, we have to calculate this correlates not in real time but in Euclidean time. So to go from Euclidean time to real time, we need to analytically continue. So this tau going to IT in real time. But as clearly mentioned in the Dibyendu's talk, that we have data points in because we have discretized the space time, Euclidean space time. So we have data points at discrete values of tau. And we moreover, when we do lattice calculation, we need to do the generation of different samples, and we have to evaluate the expectation value. So for calculating that, we have such statistical uncertainty. So when you have discrete data points and statistical uncertainty, we can construct infinitely many fitting form by fitting them. So if there are infinitely many functional forms, so for that infinitely many analytic continuation will be possible. So infinitely many analytic constants, so each analytic continuation will give different results. So to constrain this infinite dimensional functional form space, so we need to give some physics motivated input to constrain them. So which analytic continuation form will we take? So now the operators. So the static potential can be calculated from this Wilson loop. So these are the gauge links. And to calculate the spin correlator, so I will explain everything in detail. So if you focus on this part, so you have this time ordered path ordered of this WRT is the Wilson loop, and this they are inserted magnetic fields are inserted at 2 points. So the interaction part is that you have to insert color magnetic fields at two separate points which are separated by R. But for the self part, you have to insert the magnetic fields at the same line, and this will be, there will be no insertion for that, for this operator. So if you can see, there is a chi factor, x factor here. So when you calculate the total potential, you have to add this, and for pseudoscalar this is identity, and for vector channel it is -1/3. So when you add these two, the pseudoscalar and vector will get different contributions. So that will make the degeneracy between pseudoscalar and vector. This will break the degeneracy between pseudoscalar and vector. Now to find the, as I mentioned, we need to find an analytical structure to fit the lattice data and extract the potential. So if we calculate in hard thermal loop perturbation theory, at tree level, we can calculate the correlators, and this correlator gets a linear term in tau. Tau is the Euclidean time, and there is a periodic term which is log over sine pi tau by beta, and beta is 1 over temperature. So this same structure has been observed for this log of Wilson loop. So the crucial difference is there is no log in our operator, and there you need to take a log for this Wilson loop, and the same structure, the structure remains same. So now if we analytically continue from tau to it and take this limit, take this take this partial derivative and take that limit, we will get this fr minus iota times gr. So this spin potential also is getting a real part and an imaginary part. So the spin potential, this thermal spin potential will get an imaginary component. So now we have an analytical expression. So our lattice data also depends on this r and tau. So we can fit our lattice data with this expression and extract this real part and imaginary part, and we can construct this total potential. So now the origin of the imaginary potential, as mentioned by Blezo, and yeah, yeah.
What is the range of tau you can look into? Like the first formula.
Yeah.
Yeah. So the values of tau, can it start from 0?
No, it should be because we have a finite temporal extent. Let's say 30 or 32. Let's say. So we need to take the due to this periodic nature, we have to take from n tau by 2, means the half of the time extent of the temporal slice.
Okay.
And you can extend up to, but not 0 or at very large. In the intermediate range, it will valid.
Okay.
So origin of the imaginary potential, as mentioned by Professor Blezo and Dipendu, that I will mention. Yeah. So if we consider this self-energy correction of this gauge field propagator, so mu nu, and in the hard thermal loop perturbation theory, this external momenta is of the order of gt soft, and loop momenta is integrated up to this by the hard modes, hard gluons, this pi t. So if we calculate this is self energy correction in the static limit where the energy is taken to be 0 and momentum tends to 0, at leading order we get this pi 0 0 means a0 for the self energy correction for color electric fields. So this gets md square, which is of the order of g square t square. So this tells that the chromoelectric fields will be screened because it is getting a mass of the order of temperature. But if we calculate color magnetic correlate the self energy correction of the color magnetic fields pi ij, this remains 0 at leading order. So this suggests there's no color screening of chromomagnetic field, so they will be never screened. But we know from non-perturbative studies and also arguments that they do not remain 0, they gets a mass of the non-perturbatively, which is of the order of g square t, and this is also verified from lattice studies. So that this color magnetic fields doesn't get screened, but they remains confined. So now next, in the time-like region where the pair creation or annihilation type of process can occur, so where the energy is greater than this momentum, this pi, this self-energy correction remains real. But when there is a scattering-like process occurs in the space-like region, when the energy of the external momenta is less than this the 3 momenta, this pi, this self-energy correction contains both real and imaginary part. And in finite, this is known as Landau damping. So whenever we are in a finite temperature medium, there are these particles with there are already particles with momenta pi t, and when these gauge fields will interact, will scatter from these gauge fields, this will lose, the gauge fields will lose energy, and for that the imaginary part comes into account. So energy loss of gauge fields by scattering with these hard particles will give this imaginary potential. So for Wilson, as mentioned by Dibyendu, that for Wilson loop or for the static potential, and this the pi 00 component will contain the imaginary part, but for the spin potential, this pi ij pi ij will also contains a imaginary part, and from that contribution we are getting the imaginary part of the spin potential. So now for lattice practitioners, we have calculated this gauge invariant, instead of calculating the gauge invariant Wilson loops, we have calculated replace the Wilson loops with Wilson line correlators in a particular gauge, because the noise, these operators becomes very noisy, but this Wilson line correlators are less noisy, so there is a better signal to noise ratio. And these color magnetic fields are implemented by a Clover operator, which have much less discretization of errors than a placket operator. And this noise are reduced, this ultraviolet flux, there will be ultraviolet fluctuations, and these are reduced using gradient flow technique. And so we have, so in lattice we have to calculate this operator on all and at different configurations, and you need to take a expectation value. So we have calculated at up to around 2000 configuration. For we have fixed the lattice, the spatial extent fixed, and the temporal extent is varied 1620 to change the lattice spacing and to take a continuum limit from two lattices. And these are performed at a single temperature at around 470 MeV. For when there are no dynamical fermions in our study, so we have taken the dynamical fermions mass to be infinite. So these are only pure gauge fields. So now to check the we have extracted the functional form. Now these are the lattice data, the points. So this x-axis is this tau, the Euclidean time, and the y, this plot is, I have shown the correlator for self spin interaction, and this plot is for spin spin interaction. So as we can see, if we increase the distance, the self spin interaction doesn't change that much, it remains constant, and the line is for the after the fit we get the real part and imaginary part, and then I have shown the fit. So the fit are quite good, and the chi-square per degrees of freedom remains around 1 or 0.7 or 1.3 in between. And for spin part also we are getting excellent agreement, excellent fits, so for different distances also. So and I have shown this for the final lattice at a fixed flow time. But I want to mention that this we need to renormalize the operator with the the operator, and this is non-trivial. So when you do the lattice, when we are putting our theory in a lattice in lattice regularization, so this does the renormalization of the coupling, but the renormalization of the coupling is not sufficient to renormalize the color magnetic operator. And these are studied in great detail by these two references, and we have just used the same technique to renormalize our color magnetic field operator. So now the imaginary part of the spin potential. So we have two components, self spin and spin. So after extracting the real and imaginary component from self interaction, and similarly from spin interaction, we have to add and subtract the two to get the pseudoscalar and vector potential with the factor of 1 and 1/3. So this is the R in Fermi units, the distance between a quark and anti-quark pair, and the y-axis is the imaginary part of the spin potential. And this left plot is for Charmonia, and this right plot is for Bottomonia. So I have shown this eta c for pseudoscalar. The imaginary part is much larger than the Jepsi, the vector state. These are at very small distances. So we have considered the distance up to the bound state of the Charmonia, let's say up to around 0.3 Fermi, and for Bottomonia up to around 0.2 Fermi. So we can see, and this plot is the imaginary part of the static potential, the leading order correction. So we can see that the spin interaction potential remains substantially large in these short distances for both Charmonia and Bottomonia. So the first comment is the non-perturbative study confirms the perturbative prediction of the imaginary part for spin interactions, but this magnitude remains much larger. If we plot the perturbative one, this will remain at very small distances. So we need to perform this non-perturbative study, and spin potential dominates at short distances than the static potential for both Charmonia and Bottomonia. So we need to take this into account to construct a realistic spectral function. And at very short distances, this strength of the pseudoscalar and vector imaginary part is quite different. So we expect that they will have different thermal decay widths. So as the strength of the pseudoscalar is much larger, so they will get suppressed much earlier than the vector. So now, if we consider the real part of the spin potential, this self energy of the spin potential in the lattice will have contribution of two parts: ultraviolet divergent piece, and which the zero temperature part, and there will be finite temperature contribution. So to get this finite temperature contribution, we have to subtract this lattice results from this ultraviolet divergent piece. So we have calculated this ultraviolet divergent piece using lattice perturbation theory. And we have subtracted the leading order divergence from the lattice data, and we extract the finite temperature contribution. So this for spin so we have extracted the spin potential, as I said before, from the correlators, and we have added the two terms to get the pseudoscalar and vector channel. So this same the r-axis and the x-axis is the interaction, the distance between quark and anti-quark pair, and the y-axis is the real part of the subtracted potential, the self energy in the ultraviolet divergent subtracted potential, and these are for Charmonia and these are for Bottomonia. So we can see that this eta c, this pseudoscalar is getting a attractive potential, but for vector channel it is a repulsive type of interaction. And if you see this this 0.5, this correction, this is the thermal phase shift, mass shift due to this self energy correction. So for Charmonia it is around 500 MeV, this thermal mass shift, and for Bottomonia it is around 50 MeV. So yeah, and this so we know at zero temperature this spin potential is a delta function, so delta cube r. So but in lattice we cannot extract this, we will not get this delta function type of behavior, but we have calculated this in perturbation theory, how lattice regularization will change the delta function, and that matches quite well with this type of nature. So we can say this is a lattice regularized delta function behavior. So and this results doesn't change at finite temperature, only this mass shift is there. This 0 comes down to 50 MeV. So but the nature of the potential remains same as 0 temperature result. So now as a conclusion, so for the first time we have calculated this non-perturbative spin interaction potential in the finite temperature QGP medium from first principle lattice QCD study. So we have shown that the spin potential develops in imaginary part perturbatively first, then I have confirmed that non-perturbatively also the spin potential will develop in imaginary part similar to the static potential. So, and at very short distances around the size of the quarkonia bound state, spin potential gives dominant contribution to the thermal potential, total potential. So we need to take them into account to construct a realistic spectral function. So qualitatively, pseudoscalar states will get suppressed early at earlier temperatures than vector states. But to predict, quantitatively to study this, we need to solve the Schrodinger equation and calculate the decay widths, thermal decay widths, and the bound state mass. And to predict the suppression temperature exactly of the pseudoscalar and vector quarkonia, we need to perform a study for the temperature dependence of the spin dependent potential, how this changes at different temperatures, because we have only studied for one temperature. So we need to do that and solve the Schrodinger equation and calculate the thermal decay widths and bound state mass. So that's it.
Yeah, thank you, Swagatam. Yeah, can you show again the plot where you displayed? Yes, exactly. The the bottom curve is the perturbative result, right?
No, this is the non-perturbative result for the static potential.
It is a what? I'm sorry.
Non-perturbative results for static potential. For spin independent part.
Oh, it's a spin independent
Yeah.
part. Yeah, because the question I wanted to ask is there any understanding of the small distance spin potential?
At finite
You
intensity?
see, the spin independent part is easy to understand because it's this color transparency phenomenon,
Yeah.
right? The
Yes.
two color charges are
Yeah.
neutralize themselves, so to speak. Is there any simple argument for the spin potential at short distance?
Yeah, as far as I understand that when you are applying this magnetic fields on this Wilson line of Wilson loop operators, then the color singlet can go to colored octet like states, and the colored octet can have a finite imaginary part at short distances. So from that we can argue that at short distances this singlet state can go to octet state, and this transition can give a finite imaginary part at short distance. Due to the application of the magnetic fields only.
Two questions. First is probably essentially re-asking the question that Professor Blazo asked. But you also said that all these values are much, much larger than the perturbative value, even though
Yes.
does it make you nervous that you are getting at 0.04, 0.05 Fermi a result which is order of magnitude larger than the perturbative result? That's the first question. The second question was a bit more technical, but maybe the first question. I do not understand this large value. So.
One thing I can comment that this perturbative calculation are in the HTL framework, so that will not valid at very small distances. They are valid up to.
So then, okay, maybe some kind of a multiple expansion result one should compare with. I agree. HTL is not a good thing. Okay, somehow the general philosophy that you are getting such a large value of this potential, which will probably say large value of decay width or something.
No, we have not calculated it, but we.
I understand, but you are saying that it's a huge 4G, 0.4 GeV kind of decay width at 0.05 Fermi distance particles. Where the thermal gluons will find it difficult to even probe this kind of distance scale at 300 MeV. Yes?
Similar thing happened for the case of hybrid potential that we saw, right? So we have a finite imaginary part there. Also, the whole object is singlet. Right?
And we said we do not know whether to interpret it as a potential.
No, we can interpret it as an octet, right? There is.
Yeah, so we are saying basically there is no bound state formed, but here there is a bound state being formed.
But if you go to this plot, so the correlator cartoon that you have.
This?
No, cartoon, that picture with the Wilson loop and two magnetic field operator. Yeah. So at short distance, R equal to 0. This is basically the hybrid operator, hybrid.
Yeah.
Wilson loop.
And we are integrating over all insertion.
Imaginary.
So.
Question was about the total, the total potential that a singlet, what do you mean this is the hybrid potential?
So you just have, so for example, if you have hybrid potential.
Okay, we can discuss it later. I don't think this will be the hybrid potential, but we'll discuss it later. This is a singlet operator for which you are studying. But we can go through the detail. The second question was about your magnetic field operator renormalization.
Yeah.
So you didn't quite explain, but I presume once you do this renormalization, you will get a scale dependence, right?
Independence, yeah. Yeah, scale dependence, yeah.
So then what do you do?
No, so in this reference, they have explained that So to get from lattice regular, so we first we need to perform a continuum extrapolation, let's say. So we have continuum data. Then this depends on a flow time. So we have that scale. So to go from flow time to ms bar, we need to perform a, there are two different scale, ms bar scale and flow time scale. So we need to perform a renormalization group flowing to get from one scale to another scale. And now we have ms bar scale dependent operator, and we have calculated the physical correlator from that by this matching code.
So after ms bar, what do you do? So the potential is in ms bar at some scale?
No, that is physical, but we have to multiply a renormalization factor to get from ms bar to physical.
So the particular matching of the ms bar to physical that Line calculated,
Yes.
that was for a different physical quantity.
Yeah, I understand. Yeah.
That will not work here.
At very, no, it will work at very large distances, but at very short distances, this
No, that depends on the physics question. No, he's saying that for that particular physics question, this is the length scale that is relevant. And this is how you match to that. Oh, we can talk also about that later.
Okay.
But I think this will be an observable dependent matching.
Yeah, obviously. But as far as we can do it the best.
Okay. Thank you, Swagatam. So please discuss with him if you have any question. We are hungry. So let's go to our lunch. And big thanks